Today we take a break from the self-driving car project. Don't worry, it's still very much related, but finding the intersection of two line segments is such a useful tool that I wanted to teach this as a standalone video. I will refer to the car project from time to time. For example, we'll need this segment intersection to implement the sensors, and also the collision detection with the side of the road and other cars as well. So let's learn how to find the segment intersection. It will be a combination of math and coding, mostly coding, where we experiment and figure out why the math works. You're gonna love this, trust me. It's best if you follow along with me, so open your editor and let's cross out segment intersection from your must-know skills. Get it? Cross out? Because No. Gonna code, debug, and have fun. Coding with Radu, coding with Radu. Gonna prototype and design. Coding with Radu, coding with Radu. Let's code now. We begin with basic HTML. In the head, I'm gonna write the title for the page. Segment intersection. And in the body, I'm going to define a canvas element. I'll call it my canvas. And it's gonna be the only element we'll work with, really. Now, if we save and refresh the page, almost nothing happens. Here we just get this title appearing here, segment intersection. And if you open the elements, you will see here the canvas element, but it's small and it has a little bit of a margin because the body actually has this orange margin over there. So I'm going to remove these and stretch the canvas to fill the whole screen. And I'm going to just do this by adding some inline style here, some inline CSS. I don't need to open a new file just for this project. It's gonna be something that we use to understand how segment intersection works, and we're not really gonna need it afterwards. Now, with the styles in place, I'm also going to write here a bit of JavaScript, and the same goes for the JavaScript as well. We won't need external files today. And here I'm just going to stretch the canvas so that it covers the full window width, and the same goes for the window height. And we close the script tag here. Now, if I'm going to save this and refresh, you will see the canvas is now covering the whole screen here when we hover over this element. And there is no more margin from the body. This overflow here is important if you want to avoid having scroll bars. Sometimes they appear when the canvas fits the whole screen. Now let me move this JavaScript code actually all the way to the left like this because it starts to not fit in the screen anymore. And we need to draw some points. So let's define some points here. I'm going to use some coordinates for them that I chose previously. And with these 4 points in place, we want to see if the segments AB and CD are intersecting or not. So that's going to be the challenge for today. Before we start to think about the math behind all this, we visualize things just to make sure that we have the points on the screen and that there is some intersection over there. So let me get the canvas context like this. And I'm going to begin a path, move to point A like this, and line to point B. And I'm gonna do the same thing, move to point C, line to point D. So I'm drawing 2 lines between A and B and C and D. And saving the file and refreshing the page, we get some lines intersecting over there. Good, but At the moment, it's actually not clear where A, B, C, and D are, and it's going to be helpful if we can visualize them. So let me begin a new path, and with a white fill, I'm going to draw an arc at the A location with a radius of 10 pixels and a full circle. So starting at 0 degrees and math pi times 2. Actually, this is in radians. So we measure 2 pi radians, the full 360-degree circle. And let's fill this and stroke. And at the moment, this is just going to show here a small white circle with a black outline. But we can, of course, draw a little bit of text here. So I'm going to set a fill style to black and a fill text like this. So I'm going to write the A string at this location. And now, if I save the file and refresh the page, you can see this small a here. We can make it look a little bit nicer if, for example, we use text align to center and text baseline to middle. And here we have a font that I'm gonna make a little bit bigger, bold, and I like this Arial font. So let's see how it looks like now. Much better. And I'm not going to write this for all the other points, obviously. I'm going to extract the function now. I'm going to say here function draw dot, and this dot is going to get a point and a label as arguments here. And all of this code goes inside this function like this. I will replace a with this point value, and this string right here, I will replace it with the value of label, like so. And now I can just call here draw dot a with the label of a, and when I refresh, nothing changes. But now I can write here B, C, D like this. And we can clearly see where all the points are. Now, before starting to talk about this actual intersection and how to get it, I'm gonna show you how to get something a little bit easier but still related. The middle of segment AB. Let's call it M. And I'm going to write here M is equal to the x-coordinate of M is going to be found using linear interpolation. So let me just write here linear interpolation, or lerp, from a dot x to b dot x at halfway, so 0.5, and same goes for the y coordinate, like this. So this lerp function is something really easy. It just gets two values, and the third one is a percentage. It says how far you are from A, and we just return A plus B minus A times T here. And this is a very useful utility function. I've used it in a bunch of projects, and I really recommend you keep it as well and think of different uses for it. But check it out, it's really not hard. So when t is 0, this whole thing is 0, and this just stays a. When t is 1, this minus a here cancels out this other one, so you're left with b. So basically those are the endpoints. And this difference here, if you're going to take half of the difference, then you're moving away half from a. It's a very intuitive function, and this is how you can call it to get the midpoint of a segment. You call it twice, once for x and once for y, with the same t value here. This is important. So let's display now draw dot m with the string of m, and it's there. And you can try to change this 0.5 to something else, like maybe you want m to be further away from a, maybe somewhere here. Let's replace this with a value of t and set t equal to 0.7. And you can see that m is now a little bit lower this time. But let's do more than that. Let's actually animate. So I'm going to remove this t from here. And here below this context, I'm going to say let t is equal to 0. And we will animate. This animate function is going to first clear the canvas on each frame, because we will probably have something else there waiting to be removed. And then I'm going to just put everything we have here inside of this function. And at the end, t will increase by a small value like this. And we will call request animation frame with this animate function as a parameter. Let me close this animate function now, save the file, refresh the page, and you can see m moving from A towards B, and look at that, it goes away from A and B. This is now called extrapolation. Interpolation is between the points, but now it's going outside in the direction from A to B. And this doesn't need to start at 0 actually. You can start at -1 if you want, or any value really. And now you can see m following that line defined by AB, going in that direction. But when t is 0, then the point is at A, and when t is 1, the point is at B. Let me show you. So here where we are drawing the dot, I'm gonna add another value here, and I will say if t is less than 0 or t is greater than 1, then this is going to be here another argument. Let's just call it is red, and we are going to color it red right here. We will say if is red, then we will return a red color. Otherwise, we return a white color. This is a so-called ternary operator in JavaScript, and we just avoid the if statement in this way. So I'm going to save this, refresh, and you can see now m is red, but then it turns to white, and when it leaves this AB segment, it turns back to red again. Neat. Let me do the same thing for another point, n, that goes from C to D. So I'm just going to copy here m, and I'm going to call this n, and this is going to be C, C, D, D. And here we are going to draw n. In the same way. Yeah, it was off screen a bit, but you can see n also moving along the other line. And you can see that if you just use the same t for both of them, they don't actually intersect. So one small game that you can play is try to figure out what values for this t could n have and m have, so that they would actually intersect. And that's how we are going to solve this, but we are going to solve it using mathematics, not by guessing the value. So let's do this. Let's move here and try to initialize our intersection point. Let's say I is equal to get intersection AB, CD, so the intersection between AB and CD. And I'm going to draw here I on the canvas. Now below here, going to start to define our get intersection function between AB and CD like this. And here I'm actually going to start to write some math. So if we have an intersection, this intersection point needs to satisfy both of these things. So the point has to be on this line here that is defined for A and B, but it also needs to be on this other line here. And I'm using T and U here because they need to be different. We saw previously that the same T just doesn't work. We need to find out what are these values. And now I'm just going to copy this first equation here from this system of two equations. And I'm going to try to write U in terms of T. So let me now move this Cx on the left. So I'm going to subtract Cx from here, and we get Ax minus Cx plus the same thing equals to just dx minus Cx on the right times U. Now, at this stage, you could divide by dx minus Cx, and then you have U written in terms of T. But if you divide like this, there's a problem because this dx minus Cx might be 0 if the CD segment is vertical, and we don't want to divide by 0, right? So I'm actually gonna leave this in this way here and move on. I'm gonna later try to substitute this whole thing somewhere else. So I'm now going to write the second equation from here. I'm just copying it. And I'm going to subtract here cy. So I'm doing the same thing pretty much. Like this. And in this case, I'm actually going to do a trick and multiply by dx minus Cx. And you'll see why in just a second. So here we have now dx minus Cx times ay minus cy plus dx minus Cx times by minus ay times t is equal to dy minus cy times dx minus Cx times U. And maybe now you can see why I'm doing this. So this dx minus Cx times U is the same as here. So now I'm going to replace this dx minus Cx times U with this thing on the left. I'm just going to copy this, maybe align this a little bit better here, like so, and paste this here. But I need to be careful because when I paste this, this dy minus cy has to distribute inside here and multiply also like so, right? Now here I'm going to leave t on the right side. So I'm going to subtract this, and I'm also going to subtract this part times t. And when we do this, we get this. And here, factor t, and then divide by that side, and we have the value of t. So when writing t in code, I'm actually going to divide it into two parts, a top part and a bottom part. And t is going to be top divided by bottom. But remember what I said earlier about division. If you divide, that thing better not be 0. So I'm going to quickly implement this, but we will still need to investigate when this bottom part is 0. So we still have a bit to go. I'm going to now write here top is equal to dx minus cx times ay minus cy minus dy minus cy times ax minus cx, like so. It's the same thing from here, but I'm using JavaScript syntax. And same thing here with the bottom part. Now t is going to be equal to top divided by the bottom. And to return, I would like to actually return a point, like to know the x value and the y value of this intersection. So to get it, if we know t and a and b, it's easy. We just do linear interpolation again. So I'm going to say here lerp from a to b using t, and same for the y here. Okay, let's refresh. And look at that. There's another dot there, exactly where those segments intersect. We're not going to need this m and n anymore, so I'm going to remove them next. And actually, I don't need this t global variable from here either. Let's clean up this part. So now when I refresh, I have just the I dot at the intersection there. But does this really work? I mean, it works for this one example, but how about others? I'm actually gonna now move the AB segment using the mouse so that we can try a lot of different possibilities and see how I moves as I move the segment. So let me go up here and implement something like this. I will initialize the mouse to be at 0, 0 in the beginning, but then I'm going to add an onMouseMove event to the document and say that the mouse X should become the information associated with this event. And now inside of this animate function, I'm actually going to modify the locations of A and B according to the mouse and this so-called radius. So basically A is going to be 50 pixels above the mouse, B is going to be 50 pixels below the mouse. And now if I refresh, I have an error. Oh, T is not defined. I'm still incrementing it right here. Now, if I refresh, you can see that as I move AB with my mouse, I is also sliding along CD, which is nice. We still have a little bit of a problem here that I is going outside of this, so we will need to bound this to the T values so that we only show segment intersection when the segments intersect, not when the lines are intersecting like this, but we'll get to that. Another thing you might be wondering is, okay, it works, but AB is suspiciously straight. Does it work if AB would have another kind of angle? Because the reason I'm asking this is that we do have here this division by the bottom, so maybe we can break the system if this bottom becomes 0, and trying out more angles might make this system break. And we want to test these possibilities, otherwise we will make something that doesn't work all the time. So let me go here and define an angle. Let's say let angle is equal to 0. I'm using let because it's going to change quite soon. And then here, when we are updating A and B, I'm actually going to add math cosine of this angle multiplied by the radius. So using the unit circle. And for B, I'm going to do the same thing, but in reverse. So minus math cosine angle times the radius, and here plus math sine angle times the radius. And we want the angle to change on each frame. I'm going to add to this angle 0.02, for example. Save the file, refresh the page, and now we have this interesting spinning thing there. And it really looks like it works. Like, as it's spinning there, I is constantly moving, and I can move this segment pretty much anywhere, and it's going to show the intersection as you expect. So what happens? What happens with that bottom? When is it 0? Is it ever 0? Let's try logging it. I'm going to go here and say console log bottom, refresh, and the values are changing too quickly. I can't really figure it out and concentrate on that. I will visualize it soon, but you can see that sometimes they're positive, sometimes they're negative. So maybe there's going to be some transition at some point and it will be 0. So this is interesting. Let's see how this looks like. So I'm gonna stop this debugging here, and I'm gonna return this bottom here as well. And up where we are drawing this eye, we can actually get the value of this bottom and display it somehow on the canvas. I'm going to draw a rectangle that is starting in the middle of the screen. So my canvas width, half of my canvas width, and this rectangle is going to be on the top of the canvas. So 0, y, and then the width of this is going to be I dot bottom. So I'm going to animate bottom as a rectangle that is going to grow and shrink from the middle of the screen, because when it's going to have a negative width, I want to see it go in the other direction. And the height is anything. I'm just going to put here 10 like this and fill it like so. Refresh, and you can see the rectangle here, but if you recall, the values were quite large there. They were, I think, something like 10,000, 20,000. And immediately when they approach 0, they are large enough to just go outside the screen. So I'm going to scale this by, let's say, dividing by 100. And now you can see this rectangle in full glory over there. So we can do this because I'm really interested, when is this bottom 0? And I don't care if I'm scaling all the values. 0 is still going to be 0 after dividing by 100. So now with this new visualization, can we figure out what is happening? It really looks like when the segment is parallel to the other one, then this rectangle at the top just disappears. So now, no matter where I'm moving this, actually, as I'm moving the mouse, nothing affects this top rectangle over there. But when the angles are in such a way that those two segments are parallel, it means that that value of bottom just disappears. Now, because the angle value here is changing by this much, and the angles are in radians, and we have floating point numbers that are represented with some number of digits but not full accuracy there, it means we might not get 0 in this situation. But if we do, then that code is gonna break. But the good news is that if it's 0, we don't need to return an intersection. There is no intersection. So let me now remove this new code for making the bottom visualization. It served its purpose. And now here, let's really go and say, if bottom is not 0, then we can get the value of t. That's okay. And let's make it be between 0 and 1 as well. So if t is more than 0 and t is less than 1, then we are going to return something. Now, in the self-driving car project, I actually like to return two things. First, it's the x and y value of the point, but I also like to return t as an offset. Because when the sensors of the car are reading something, I would like to know how far from the car this object is. In these other cases, if the code reaches here, we just return null. And up here, I can't draw a point that is null. So if there is an eye, we are going to draw the eye. And I'm going to save this, refresh, and you can see now eye is appearing there. But if the segments are not intersecting this time, then eye is not there. So the intersection is now not between lines, but between line segments. Or at least one segment and one line, because if I go here, you can still see that I is appearing. And that's because the U value also needs to be checked and also needs to be between 0 and 1. Otherwise, we have this weird situation where maybe CD is like a laser pointer shining at some spinning thing there, and you see exactly where the point of intersection is. So CD just goes on infinitely. This is now collision between intersection between a line and a segment. So let's wrap things up. To calculate the value of u, we are going to need to know the equation of u. And it's actually very easy to get in a similar way that we got the equation for t, but I'm not going to do it. So that's going to be your homework. I'm just going to show you what the result is. And the good news is that this bottom part of the value for u is going to be exactly the same. So great, we also know that it's not 0 unless they are parallel. But the top part is different. So I'm going to write it here, and you should check your math if you come to the same value as I do right here. Okay, and let me rename this to t top. So this is going to be t top, t bottom, and for u we now have u top divided by bottom. Actually, it's the same bottom here, and I need to check if we are between those 0, 1 with u as well. Like this. And now we save the file, refresh. I is here, I is not here, or anywhere else than at the segment intersection. Now, when mathematicians talk about this, they often use more advanced terminology. You may hear words like linear algebra, vectors, matrices, dot products, determinants. In my experience, students get scared when they hear things like that, so I tried to avoid them in this video. But they are important if you want to become better at math. So I'll add a link to a more mathematical approach I found online. Check it out. And I also urge you to think why I teach it in this way, by combining math and coding and how I use visualizations to figure stuff out. And think if you can use the same approach to figure out other stuff as well. See you guys.